just recalling the basics, and by the basics, I pretty much mean the definition actually of operator spaces. Then I'm going to talk a little bit about coarse geometry, just mentioning what are the kinds of embeddings and equivalences that a coarse geometry looks at. And then I want to talk about how to try to mix those two things together. And as you guys are going to see, there are three approaches I'm going to present here. One of them fails miserably. The other two, we do have some positive things to say about it. So let's start. Oh, and some of the results are going to be joined with people, but I will mention when that's the case. Okay, so operator spaces. So the very basics here. So throughout this talk, H is always going to be a Hilbert space, and B of H, the space of bounded operators on H. And by an operator space, what I mean is a closed linear subspace of B of H. Okay, so every time I'm talking about an operator space, I am fixing some H, and I'm thinking about this guy as being inside of B of H. So if anyone here is not very familiar with operator spaces, you guys may be thinking, well, then what is the difference between an operator space and a Banach space, right? Because obviously a closed linear subspace, a Banach subspace of B of H is a Banach subspace, is a Banach space. And if you have a Banach space, of course, it sits inside of some B of H linearly isometrically. So aren't we talking about the same objects? And sure, we are talking about the same objects, but actually for us, what changes when you're talking about operator spaces is not really the object itself, but the morphisms you care about, right? When you're talking about Banach spaces, you're interested in, at least if you're doing the linear theory of operator spaces, of Banach spaces, you're looking at bounded linear maps between them. Here, we won't be looking at bounded linear maps anymore. We want something stronger that actually takes in consideration not only the space X itself, but actually how it is sitting inside of P of H. So let's just quickly see how this is done here. So let's say that you start with a set X and a set Y and some natural number N. So by M and X, I'm just denoting the N by N matrices with entries on X. And we're going to be denoting elements in it by things of this sort. Okay, so I have a square matrix in which each entry here is an element of my set X. And if I actually have a map between X and Y, this map also generates canonically a map from the matrix spaces of X to the matrix spaces of Y. And this is done by simply computing this coordinate entry-wise. And this map here, F sub index N, is what it's called the nth amplification of your map. Okay, so now let's say that you actually start with an operator space. So it's sitting inside of some B of H. Now you are looking at the matrices spaces on X, and you want to see each one of those guys here also as a Banach space. So you also want to have some norm on this space. And this is done in this very natural way here. So what is this? So since X is sitting inside of B of H. Okay, so we look at this B of H. You can take L2 sum of n copies of H. This is what Hn is. And then you still have a Hilbert space. So you can look at the bounded operators on this Hilbert space. So here you have the operator norm in this Banach space. Okay, so since those two things here, taking Mn of BH or B of H to the N, they are algebraically isomorphically, you can actually transfer the norm that I have in B Hn to this little person over here. So this comes endowed with this natural norm. And since X is a subset of B of H, Mnx becomes a subset of Mn BH. So this comes in here, with endowed with this norm here, just as being a subspace of it. Okay, so with this background in mind, let's now define what completely bounded maps are. So now you start with a map, a linear map actually, between operator spaces X and Y. So if you look at the amplifications as I had in the previous page of this map, since F is linear, Fn is also linear. So we can talk about the operator norm of Fn. And now what we do is we define what is called the completely bounded norm of F to be the supremum of all such norms. If it happens that this is finite, then we call the map not only bounded, but actually completely bounded. And that's the notion we look at when dealing with operator spaces. So just as we define isomorphisms, we can also define complete isomorphisms, right? So what is this? This is just a linear bijection between the spaces such that both the map and the inverse are not only bounded, but they are actually completely bounded. And if you want to talk about a complete isomorphic embedding, well, the same thing, right? It's going to be a complete isomorphism with a subspace of the target space. Okay, so those are what operator spaces are. Now let's just quickly recall the very basics here of coarse geometry. So in here, I'm just looking at arbitrary metric spaces, but of course, we're going to be looking at operator spaces, or at least subsets of operator spaces in what follows. So you look at operator spaces, X and Y, and you consider a map between those. So you have those two moduli over here. Right? So this omega F is telling you how much the image can be far away from each other, given that the points in the domain were at most something away from each other. And here is the opposite. It says how much the points in the image must be far away from each other, given that the points in the domain were at least something specific away from each other. So with those two, with this moduli, we say that the map is coarse if omega F is finite, for omega Ft is finite for any t. So this is saying that given a specific diameter t in the domain, if I look at the image of a set of diameter at most t, my image will have diameter at most omega Ft. So I'm sending bounded things to bounded things, and in a uniform way where the uniformity is given by this modulus here. Okay, but this is just a coarse map. If you want now the map to be actually a coarse embedding, you want the map to be coarse, but you also want the inverse, and with some quotations here, because it's not really an inverse, right? But you also want the inverse to satisfy a coarse condition. And this is what I call the map itself to be expanding. So here it's saying that if you want to map things to things which are very far away, that's okay, as long as you start with things that were already far away as well in your domain. And now for coarse equivalences, we just want, what is a coarse equivalence? It's just a coarse embedding whose image is very large in the codomain. So we don't really care here in coarse geometry if the map is a bijection or not. That's not important. It doesn't need to be injective, it doesn't need to be surjective. But we just want this largeness condition here to be satisfied. So you want the image to be let's say an epsilon dense in the codomain for some epsilon. And just very basic examples here. So in coarse geometry, you don't really care about what is happening in a small scale. So any metric space with bounded diameter is automatically coarsely equivalent to a single point. And if you want some example which isn't of bounded diameter, Z and R, if you just consider the inclusion from Z into R, this is a coarse equivalence. So it takes care of the general shape of the space in a large sense, but not really locally. Okay, so now how can we define actually some interesting coarse theory for operator spaces? And of course, interesting here will depend on the person, right? But I would say that there is one way which is a pretty natural approach, which is just to proceed just as we just did a couple of slides ago with completely bounded maps. Let's try to do the same with coarse maps. So you start with a map between operator spaces. Now we don't care about the map being linear anymore. So just as we did with the norm, right, with the norm of the FNs, we look at each amplification. Each amplification has this omega F and module defined, and you can look at the supremum of all of them. And you can say that this is completely coarse if it actually is finite for any t. Here I'm just unfolding the definition, okay, in case someone wants to see what this is. So I'm just saying that there is this uniformity, and for every R, I choose some S, and I'm sending points which are R close to points which are S close, and this should not depend not only on the points, right, but on N either. So this would be a very natural way for you to try to generalize a coarse notion to an operator space, but this actually fails miserably. This doesn't work. So as I have here in this result of Alejandro Chavez Dominguez, if you start with a map between operator spaces, which is completely coarse, so a priori this map has, it keeps no track of the linear structure at all, but actually happens that the map is automatically at least R-linear. And not at least R-linear, a translation of an R-linear map. And here, just one thing, just a quick comment. Throughout this talk, I'm intentionally leaving out the scalar field here. You can consider complex operator spaces or real operator spaces. The only part in which actually being R-linear here is important is here. We cannot conclude this is going to be C-linear, but we conclude this is going to be at least R-linear. Okay, so this is not a good notion, right? You start trying to do nonlinear geometry, and you conclude that the morphism you define is automatically R-linear. So that's a big fail. So what can we do? What is the different approach we can try to follow? So for that, what we did was to try to generalize, to weaken not the condition of the map being completely bounded, but something weaker than the map being completely bounded, which is the following here. So you start with two operator spaces. And now, instead of looking at one map from X to Y and demanding that not only, we care about embeddings, right? So here I'm giving a definition of embeddings here. So instead of caring about the map being an isomorphic embedding and all the amplifications to be also isomorphic embeddings and the distortion to be bounded, we do that like this. So we don't care about one single map. We look at actually a sequence of maps from X to Y. And in each one of those elements in the sequence, we just want this map to behave well up to some level of the amplifications, right? So you want, once you amplify F upper index n times, sure, you want it to be an isomorphism with a bounded distortion, let's say of K. But if you go to n+1, we don't know what happens anymore. Maybe the distortion will get very bad. So that's a completely trivial remark. This is obviously a weaker, at least formally, it's a weaker notion than complete isomorphic embeddability, and actually is strictly weaker. We can actually come up with examples of things which almost completely isomorphic embed, but do not completely isomorphic embed. Okay, so our plan then is to try to proceed just as we did in the previous slide, to write the natural coarse version of this statement instead of complete isomorphic embeddability, and then see if this is going to lead us somewhere. So this is what we have here. So we say that X almost completely coarsely embeds into Y if. So now, again, we don't want a single map F to Y, which is a coarse embedding, and all the amplifications are coarse embeddings, and you have this happening in an equi way. We want a sequence of a function, from X to Y, such that this sequence of amplifications are equi-coarse embeddings. And here I'm just unfolding the definitions as well, right? So what is this saying? This map Fn, you have those moduli omega and rho, which do not depend on n, and you want rho to go to infinity as t goes to infinity, and you have this inequality over here happening for all n. Okay, so we have this now new notion of coarse embeddability, but of course, it may be the case that this also leads us nowhere, right? So is this interesting now? And again, what is interesting, right? But I would say that for a nonlinear notion to be interesting, there are at least two things that should happen. One of them is this linear notion needs to be actually strictly weaker than the whatever linear counterpart it has, right? The existence of one nonlinear embedding should not imply the existence of the linear embedding. Otherwise, at the end, it won't be very interesting. And the other notion is that it cannot be too weak. You cannot say that everything embeds everywhere, right? It does not record. It's not capable of recovering any aspects of the linear structure. Otherwise, again, you made things too weak and uninteresting. So can we say that our new definition satisfies those two items? Well, happily we do. I'm not going to mention much about it. I'm just going to give some quick examples here because I want to talk about a different notion of embeddability. But for item 1, we can actually, using the machinery of Lipschitz free spaces, we can actually come up with examples of operator spaces X and Y, so that X almost completely coarsely embed into Y, but X does not embed into Y, not even as a Banach space. So in particular, it does not embed almost completely isomorphically either. And for 2, there are actually several examples we have for showing that the geometry is preserved sometimes. Let me just mention one here, which is this one. So if you have an infinite dimensional operator space and you assume that it almost completely coarsely embed into PCA's operator space, operator Hilbert space OH, which I won't give the definition of what OH is. It's a operator space which is completely isometric as a Banach, sorry, it's isometric as a Banach space to literal 2, and satisfies some nice properties. So it's the L2 version, is the non-commutative version of L2 in operator spaces. And if an arbitrary operator space almost completely coarsely embeds into OH, then actually needs to be completely isomorphic to OH. So this nonlinear notion actually does keep track of the geometry of OH in this very strong way. Okay, but there are actually, let me just come back here. There are actually 2 problems. So as I said, those are the, let's say, the minimum 2 conditions we would like to have for this non-embeddability thing to be interesting, but there are obviously more items you can add here. And I want to add one item which respects to this thing here. Unfortunately, the only examples we can come up to show that this is actually a strictly weaker notion are non-separable examples, which is a bit frustrating. So can we come up actually with separable examples? This would be one thing we would like to do. And the other thing is that at least we cannot come up with examples of nonlinear equivalences, which are not trivial, of course, but only of embeddings. So how can we try to fix those 2 problems? And this is the third notion I mentioned that I want to introduce here of, let's say, an operator space coarse embeddability. So this notion here, it's pretty similar to the one I had before, but now I have my maps defined only on balls, okay? And that's why I'm just adding this word here to the definition. So now I'm not talking about an almost complete coarse embedding anymore, but an almost complete coarse embedding of bounded subsets. So we say that given operator space X and an operator space Y, we say that the bounded subsets of X almost completely coarsely embed into Y if now you have the sequence of maps, but not from the entire X, just for those balls into Y. And you want those amplifications here to be equicoarse embeddings. Okay, so this is, okay, so first thing, we have now this notion, and of course, question 1 and 2 still need to hold for this, otherwise we are doing something silly. So let me just quickly observe that this actually is the case. For this notion being strictly weaker than its nonlinear, its linear version, it's trivial, right? Because this is actually weaker than the nonlinear embeddability I just presented before. So if the nonlinear embeddability I had before was already strictly weaker, so is this. So that one is fine. And for the question of whether this notion is not too weak and it still captures some of the geometry, actually the same result on OH minus some simple modifications, we can actually retain the same result for this. So if you have an operator space X and the bounded subsets of it almost completely coarsely embed into OH, actually X needs to be completely isomorphic to OH already. Of course, an infinite dimensional space. Okay, so what about new things then that we can do with this notion? So let me just mention another preservation of the geometry here that happens with the row and the column space. So for this, let me just quickly recall here what they are. So if you look at little L2 and you look at the bound operators on little L2, you can always think about them as unit matrices. And the row space is the space consisting of all the bounded operators on literal 2, such that once you look at its representation as a matrix, all its rows are 0 except the first one. And the column space, the same thing, but the first column doesn't need to be 0, but all the other columns need to be 0. So they are both, as Banach spaces, they are both just literal 2. But as operator spaces, the structure changes quite a bit. Here now, again, because of time, I cannot really mention what the interpolation is. So I'm just going to leave it like this. For any theta, this is going to be a different operator space. And I'm just going to mention that those operator spaces are all Hilbertians. So they're all just as Banach spaces, just literal 2. And if you don't know what the interpolation spaces are, just consider theta equals 0 and theta equals 1, because then in this case, you have this nice equivalence here. So you can just consider this case specifically. But what the result I want to mention is that if you have two different indices here, theta and gamma, and you look at the theta interpolation and the gamma interpolation, then they are actually incomparable with respect to this weaker notion of coarse embeddability. Okay, so this is a family of spaces which, as a Banach space, they are just literal 2. So nothing is changing. They're actually the same space, but as operator spaces, they are different. And this weaker notion actually is strong enough to capture the difference in the operator space structure of those things. Okay, and now what about the two problems 3 and 4 that I wanted to fix, right? I wanted to have examples of equivalences, not only of embeddings, and examples happening in the separable world. So let's see here. So first, what would be the equivalence, right? I didn't write it before, but this is what I'm calling an equivalence in this scenario here. So I'm considering now a sequence of bijections from X to Y. And I'm considering that once you restrict to the balls, you're restricting F and GNs to the balls, you have equicoarse embeddings. I know that's, I mean, that's not the prettiest definition ever. There are too many indices here, but well. So in this, what can we do? So this gives us a solution for 3 and 4 in the following way. So I can find separable operator spaces X and Y, so that X as a Banach space does not embed into Y, but actually they do have the same bounded subspaces, bounded subsets, sorry, almost completely coarsely. And I'm going to mention a little bit about how to obtain this result here now. I'm going to give the method. That's actually a method of Calton. I'm not going to say anything about why the method works, but I'm at least going to show you what the method is. Okay, so how can we do this thing here? So you start by looking at a quotient map. Okay, so you have two operator spaces, Y and X, and you have a completely bounded map from Y to X, which is also a quotient map as a Banach space. Okay, this, if it's a quotient map as an operator space, even better, but we don't care about that. It's not necessary. So now you can give this sequence of equivalent norms to Y by defining it like this. Okay, so I'm looking at this multiplication here, this scalar multiple of the norm of Y, and then I'm considering what happens in X by Q like this. And this not only gives us a equivalent norm on Y, but actually gives us some equivalent operator space structure on Y, which you can define it like that. Okay, this is going to give us a way for us to compute the norms in here. And well, I didn't mention, but for you to actually show that this gives rise to a nice operator space, of course, you use Ruan's theorem, but let me just skip the details here. But this does indeed give rise to an operator space structure on Y. So now you have this sequence of spaces, of operator spaces, Ym, and each one of them is not completely isometric, but completely isomorphic to Y. So what we do now is you look at the L1 sum of all those spaces. When you look at the L1 sum of all those spaces, let's call this ZQ following Calton's notation. you still have this natural quotient map from ZQ to X. And what we can show is that, well, here I'm just repeating everything. I start with the operator spaces X and Y. I have a completely bounded map, which as a map between Banach spaces is also a Banach quotient. Then I consider the things above. Then those two spaces here, regardless of what the space, what the quotient map you started with is, they have the same bounded subsets according to almost complete Coarse equivalence. And oh, actually, I should have mentioned, but I didn't. This is actually the method that Carlton used to provide the first example of Banach spaces which are coarsely equivalent to each other, but not uniformly equivalent to each other. But okay, so once you do that, then you have this property here. So now if you want to have that those two spaces are far from each other, right, like different from each other in any other way, so for example, linearly, you just need to play around with which quotient maps you have, so you can actually guarantee that they are not equivalent to each other in whatever notion you want. And well, whatever you do, they're always going to be equivalent to each other in this specific notion. So if you want to have spaces X and Y, which are equivalent with respect to this nonlinear notion, but let's say this space here does not embed into here as a Banach space, one thing you can do is you can just start with a quotient of L1 onto C0, and this will be enough. Because here then X would be C0, but this would be a sure space, since it's a L1 sum of isomorphic copies of L1, and then you would have this incompatibility. Okay, but there is actually, let me just go back a little bit to emphasize that part. So there is actually in this result that I just spent some slides talking about, there's something a bit frustrating, at least to me, which is this first item here. So sure, those two spaces we obtain, they are equivalent with respect to this nonlinear notion, and they are not with respect to the linear notion. But the restriction to linear embeddability actually happens in the Banach level, which I mean, it's nice to have restrictions which are actually truly operator spacey, right? So can we actually come up with examples in which the problem is not happening in the Banach level, but actually in the operator space level? And actually we can in a way, although as I will mention in the very last problem, there is still something I can't do. So how to come up with an operator space restriction here? So one way of doing this is to look at the space R intersect C. So here I'm just giving the definition of R intersect C. Okay, so what is R intersect C? I am looking at R, I am looking at C. I take the the direct sum of them with the max norm. This becomes an operator space. And now I look at the image of little L2 inside of R plus C, where those maps here are just the canonical maps, the canonical linear isometries with R and C. So this is the image of this map is a subspace of R plus C. And this subspace is what we call R intersect C. Okay, so with this subspace, it's known in the literature that you do have actually a complete quotient map from L infinity to R intersect C. And we actually can prove, and okay, I should have written here, this is actually a result that was obtained in a conversation with Timur Oikberg. So I apologize for that. And okay, let me just say, so here is what my ZQ will be, right? So what we're doing here, we show that R intersect C cannot embed completely isomorphically into any L1 sum of spaces which are isomorphic as Banach spaces to L infinity. Using this result, we can obtain this thing here. So we can find operator spaces X and Y, and this time they're not separable anymore, unfortunately, but we can find operator spaces X and Y, with the property that, so now in the Banach level, they are good. X still isomorphically embeds into Y. But they do not, X does not isomorphically, completely isomorphically embed into Y. And they still have equivalent bounded subsets according to this nonlinear notion. Okay, so this is still not exactly what I wanted. I would like to have a strengthening of this result, which is this missing example I'm listing here. So problem, can you find operator spaces X and Y such that X isomorphically embeds into Y, but X does not almost completely isomorphically embed into Y, but so that this is the case. And this almost word here, I couldn't do yet. And that's it. I don't have time anymore. Thank you.
Thanks, Bruno. I always appreciate refreshing the definitions of operator spaces and all these morphisms. So I speak for myself in that.
Thank you. Because I always feel like I spend way too much time in the beginning, but then if I don't do that, I feel like I'm cheating.
Are there any questions?
I have a question. I know.
Hey, Mark.
Hello. So I know you have some papers concerning the complexity of, in the sense of invariant descriptive set theory. So I wonder whether you were thinking about the complexity of your equivalencies given during this talk.
Actually, no. It never crossed my mind to right now. No, I haven't worked with that. No.
So even for completely bounded isomorphisms, right? You don't know what is the complexity of this relation for separable, I mean, operator spaces.
I honestly never thought about it, but I would imagine for complete bounded isomorphisms should be not much different than the ones in the Banach space scenario, right? But to be honest, I never thought about this question.
I think there's a paper about it. There is a paper of Sabok, Kalantar, Kennedy, and so on the complexity of completely bounded isomorphism for operator spaces.
Okay, and do you remember, does anything different happen from the Banach case?
I think it's the same. Yeah.
Okay.
And
sorry, can you say the name of the author again, just for me to take a look?
I mean, there were like 6 authors because I think it was a result of some Banff meeting. So I remember Marcin Sabok,
okay. This one is
Kennedy, and Martina Lupine.
Okay, thank you.
Yeah, so if I can, I'm just wondering to ask if you need to work in the generality of coarse maps, or you can, like in the Banach case, you can replace it with some almost completely quasi-isometric maps, right? Because in the Banach's case, coarse embeddability implies quasi-isometric embeddability, right?
So sorry, you're just asking like to change coarse by other notions, like I don't know, uniform or Lipschitz or Lipschitz.
I mean, let's say if coarse automatically implies some quasi-isometric.
If you're talking just about the map itself being coarse, yes, it will be in the same way. It will be coarse Lipschitz as well, or as you're saying, I guess quasi isometry. Sometimes people say, right? Yes.
Okay. And is it true also, like in the Banach case, that if you have, let's say, 2 almost completely coarse isomorphic operator spaces, then some ultra powers are completely isomorphic or something?
So yeah, so what actually, this is a good thing. So this is actually how we do. Sorry.
This OH, right? This proof with OH.
Yeah, the OH. We do that with ultra powers, exactly. Yeah. So this, sorry, let me get there somewhere. I will eventually get there. Did I pass? I think I passed. Yes, okay. So this OH thing here is doing exactly like that. We are looking at even this weaker, this stronger result here. We're doing exactly with ultra powers as you're saying. You're taking the ultra powers of those maps here. And in the ultra power, it's going to be defined everywhere. And you can actually get a map, which is just as you have for Banach spaces, which is going to be a Lipschitz embedding into the ultra power. But since you have now something very complete Lipschitz embedding, and since you have now a complete Lipschitz embedding, because of this other result of ours here, the map actually needs to be R linear, and then you have the embeddings you want. But yeah, that's the gist of what we're doing for OH. That's how we get this very strong complete isomorphic embeddability to OH. So yes, you can play around with ultra powers just as you do in Banach spaces.
Thanks.
Thank you.
Okay, are there any more questions? All right, thanks. Thank you, Bruno.
Thank you all. Nice to see the friendly faces of Marek and Michael.
Yes. The next speaker is